Good morning. This is legal GNSS spoofing and its effects on autonomous vehicles and Breakers GHI with Victor Murray. Before we begin, stop by the Business Hall in Mandalay Bay, Oceanside and Shoreline Ballrooms on level 2 during the day for the welcome reception at 5:30 tonight. Black Hat Arsenal is in the Business Hall on level 2. Join us for the Pony Awards in Lagoon GHI at 18:30 or 6:30 if you're an American. And thanks for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. So, Victor.
Hello, everybody. I'm so excited to be here. Happy to tell you about some of the work that we've done. Global Navigation Satellite Systems. These are constellations of satellites that orbit the Earth, broadcast a signal down, and our receivers or our phones are able to calculate their location within a certain area. And this is used for all kinds of things. I took an Uber from the airport to get to Mandalay Bay. It uses GNSS. It's also used for things like time-stamping stock trades, so they know exactly when a stock trade went through. It's also used to set the frequency of power lines. One of the issues with GNSS is it lacks integrity mechanisms. This means that all of our receivers are susceptible to spoofing. In addition to lacking integrity mechanisms, GNSS is also transmitted at a very low power. So the actual power received by your receiver is going to vary depending on the altitude, the atmosphere, things like that. But typically for GPS, the power that's received is between -120 dBm and -130 dBm. My software-defined radio that sits on the bench, very low power, is able to broadcast at +15. That's at least a delta of 135 dBm. It's a huge difference. Very easy to overpower the signal that comes from the skies. The signal that your receiver receives is actually below the noise floor. They're also susceptible to interference. So things, if the signal's reflected off of a building or a mountain, it can affect the localization estimate. If you drive under or through a tunnel or under an underpass, it can block out some of the satellites or it can block them out altogether. Similar effects with weather. So how could systems respond to spoofing? There's been a lot of good work in this area by a whole lot of people, but I'm going to highlight a couple here. Dr. Todd Humphreys, he's from the University of Texas at Austin, has had several publications that I've enjoyed reading. And this is just one example video from YouTube of them doing a live over-the-air spoofing of a drone. So what happens is the drone goes up, it's flying on its own. They spoof the GNSS signal, they get it to latch onto it. As soon as it latches onto the signal, they run the altitude through the roof. The vehicle responds by coming down. Team Unicorn did a great presentation at DEF CON on their low-cost GPS simulator. All they needed was a $400 software-defined radio and a laptop, and they were able to spoof GPS over the air, or GNSS. One of the cool things that they did was exploitation of geofencing. So the drones today come with pre-programmed areas that they're not supposed to fly, such as military bases, things like that. So what they did was broadcast a signal, making it think that they were in one of these spaces they're not supposed to be and causing the drones to come down. Pretty neat. Another interesting case is the Iran hack. So Iran claims, this is back in 2011, Iran claims to have hacked the GNSS for an RQ-170 drone, causing it to come down. There's a whole lot of things that would have had to have been set up in a very specific way for that to have happened. It's certainly possible. I don't know if it's true or not. I'm going to tell you a little bit about my experience with drones, and in my experience, it's just as possible that they just jammed the signal and it could have had a similar effect. So what can happen if systems aren't tested for GNSS issues? I was hired at my current company in 2002 to work on drones as a student. I built our autopilot system and ground control station. This picture, the one on the left, is me in 2006, and on the right's Angel Rivera. We were project managers for our flight control system. Part of my duties was to oversee field operations, and we had around 50 drones that had been built and were flying regular, so we had a whole lot of flight hours accumulating. So when the customer would have a problem, the company that owned the drone, when they had a problem, they would call me. They'd send me the data, I would look at it and do a root cause analysis, try to identify what caused this issue. Simple things from the kinds of issues that they would call me for were just a warning popping up, or the chute deployed. There's a small chute in this drone. It ended the mission early, or in a couple of cases, the drone went down and crashed or was lost. So when I was looking at these problems, there were two primary causes. The first was mechanical issues. So this is a wire came loose, or an antenna came loose, or a motor stopped working, those kinds of things. The second most common issue was with sensors. We saw issues with all kinds of sensors, but the most common was GNSS. There were instances where the GNSS would move to the right by 200 meters, or the altitude would jump by 50 meters, or we would lose it. It would drop out for 3 or 4 minutes, or we would lose GNSS permanently. The system always responded in a little different manner, sometimes appropriately, sometimes not. Sometimes the system would fly, if it lost GNSS, it would fly a little higher to try to get a better signal, receive that signal, and then go on its mission. But sometimes we lost the aircraft. So these corner cases are kind of key to improving the reliability of autonomous vehicles. And so what we thought was, let's build a system that allows us to test these corner cases, these things that you're going to have to go out and drive your car or fly your drone for thousands and thousands of hours to see just once, but be able to repeat it over and over again. So with this concept in mind, we applied for and received internal research and development funding from our company. All the results that you're going to see were 100% funded by our company. So I'm going to tell you about the spoofing system. It's got hardware and software components. I'm going to tell you about our autonomous vehicle fleet, and specifically the vehicle that was tested. Then I'm going to highlight some of our testing results. We did a whole lot of testing, but I've got 3 key ones that we're going to highlight here today: position translation, velocity manipulation, and halting the GNSS signal. And then I'm going to provide our recommendations and takeaways. We have an entire department that focuses on research and development of autonomous vehicles. All the vehicles shown on the screen here are owned by my company, and they have all been outfitted with our own autonomy kits. So the Lincoln MKZ in the upper right was also outfitted with an autonomy kit, and it's what we use for all of our testing. All of the testing, it was configured to drive by GNSS waypoint for the purpose of these tests. All the attacks that we're going to show were performed remotely and in real time. So the first word in my title is legal, which I haven't talked at all about yet. So to be legal, how do we comply? Let's start with what's illegal. Spoofing RF signals, not limited to GNSS, any type of RF signal is illegal in the United States per the Communications Act of 1934. So what's legal? Well, the FCC has a couple of routes that you can take to get special permission. You can either get an experimental license, or you can get a waiver of the FCC's rules. For all of our testing, we did not use either of those. We did not get special permission from the FCC. The next 2 items we did use. You're allowed to rebroadcast inside of a fully enclosed Faraday cage, and the key word in the regulation is fully enclosed. You're also allowed to broadcast in the ISM bands, your 900 megahertz, 2.4, or 5.8 gigahertz, as long as you keep the power below 1 watt. So the system that we use throughout all this testing is 100% legal. So this is the hardware outline. We start by putting our own RTK high-precision GNSS receiver on top of the receiver that we want to spoof. That way we know its actual position in real time. That sensor sends NEMA sentences to the computer, and the computer is able to manipulate those or pass them through unmodified. That modification, that manipulation, is controlled remotely over either a Wi-Fi or cellular link. The modified or unmodified signal is then sent to the software-defined radio, which generates the analog signal that's sent to the receiver under test. Now, the way we sent it to the receiver under test, we did 2 different methods. One was inside the fully enclosed Faraday cage, and this is, we put the actual antennas inside of a box, we put some RF dampening material in there, And we broadcast. It's over the air, but it's completely contained. And second was just connecting directly in line with the antenna. All of the testing results that I'm going to show use that approach, use this hardware outline. We also demonstrated the ability to use frequency translation. What that did was we added 2 boxes to this block diagram, one at the output of the software-defined radio and one on the receiver under test. We focused on GPS L1 band, which has a carrier frequency of 1.575 gigahertz. We then mix that with a 660 megahertz signal, filter, amplify, and it shifts it to the 915 center frequency. We send that signal over the air. This is in the unlicensed band. We then have our own box on the other side that receives that signal, shifts it, it does the opposite. It again mixes it with 660, slightly different filtering and amplification, and sends that signal to the receiver under test. And it worked. And the benefit of this was going to be we could take a lot of equipment off the vehicle and have a lighter package. The problem was when we took it out to the field, we had severe range limitations. We could only broadcast this method. It injects a lot of noise into the signal. And when we did this, we could only broadcast staying under the 1 watt up to about 200 meters. And so all the results that you're going to see use the Wi-Fi or cellular link. This is our controlling software. The software on the right is ours. It's written with Python scripts. The concentric circles, you're allowed to click anywhere, the operator can click anywhere on that screen and instantly insert an offset. That offset's scalable. It can be 1,000 meters, 100,000 meters, or it can be 1 meter. At the bottom, there's a bunch of buttons. Those are our attack scripts that do the other manipulations, messing with velocity or timing or those kinds of things. The software to the right is commercial off the shelf. It's Skydel SDX. We use that software to take a latitude, longitude, altitude position and translate it to the signal that goes to the software-defined radio. All right, the fun part, the attacks. All right. All the videos that I'm going to show, the car first drives the path that it's planned to drive. For the offset attack, we were able to manipulate the vehicle's position up to 10 meters at a time. For this demo, we offset it 4 meters to the right. And you can see the vehicle responds by moving 4 meters to the left. We then remove it, it comes right back to the right. Now understand, the signal that the car is receiving, it's driving straight on its path that it's supposed to, and then it jumps over, and it immediately corrects. So if you looked at the path that it's going, it's down it's straight down the road, except for when we inject those manipulations. Now we can modify this multiple times. We can move it 4 meters to the right, then 4 meters to the right, then 4 meters to the right. If we moved more than 10, the receiver lost fix. And understand, this car is relying on the GNSS receiver to guide itself. So if it loses the signal for more than a second or so, it kicks out and asks the operator to take over. So for us, that killed the test. If we got to that point now, we might as well just jam the signal, right? All right, besides moving it left and right, we could also move it forwards or backwards and cause the vehicle to either turn early or turn late. All right, next we dorked with the velocity. In this demo, the car comes up, it makes a right-hand turn, and it comes to a stop. For the attack, as the car is coming towards us, right before it starts to make the turn, we increase the velocity. So the car's GNSS signal keeps driving straight past the camera. Now the car still turns, because that's what its control system will do, but it doesn't see the turning in its feedback. So it turns harder, it drives itself off the road. So had we modified it earlier, for this demo we modified it right before the turn. Had we modified it earlier, it would have made a similar turn, but we could have made it turn early or turn late. So if we sped it up, the car would have turned before the turn. And if we slowed it down, it would have turned after the turn. When it's driving straight and we changed the velocity, it had no immediate impact. And the reason is because the car governed its speed based on wheel speed, not GNSS velocity, which makes a lot of sense. The wheel speed is super constant, where the GNSS velocity is a little more squirrely. All right, now the halt. For this scenario, the car drives straight through the intersection and past the camera. Okay, now for the attack, as it's coming up to the intersection, we quickly stop the GNSS signal. The car swerves right, and then it swerves left. So what actually happens is during that slowdown period, and the slowdown period is about 2 seconds, it goes from about 25 miles per hour down to 0. And when it's doing that over that, and this is the GNSS speed, not the vehicle speed, when it's making that transition, the vehicle has no noticeable effect. It keeps driving straight. But as soon as it's stopped, the control system becomes unstable. Again, the car's driving and it has no feedback. It doesn't know which way to turn. So we did a lot of other testing, and we had similar results when we did one of our timing attacks, where we passed through the real GNSS signal, but we delayed it by a couple seconds. So in doing that, the control system again became unstable and had similar results. So these are our recommendations to enhance safety critical systems. Now I'm not making these recommendations for your navigation system on your car. If you're driving down the road and your navigation system gets spoofed, what happens? It's annoying. You might be late. You might not be able to find wherever you're going to. But you're okay. There's no harm that comes to you. There's no harm that comes to your car. So these recommendations are for systems that are making safety critical decisions that can have the ability to either harm a person or an asset. So first recommendation is the easiest. That's to use multiple constellations. Most receivers already do this. It's just good practice. If you take it a step further, you can also compare the localization estimate between the different constellations with each other and look for a divergence. The downside is it's also the easiest to overcome. We're able to spoof multiple constellations, as are most security researchers that work in GNSS. All right, next, don't rely solely on GNSS for safety critical systems. All right, it's not if, but when. They will be spoofed, they can be spoofed. The cost of these systems is dropping every day. You can't rely solely on it. All right, third is to monitor the signal. There's all kinds of data that comes from it. You get position, velocity, acceleration, signal-to-noise ratio, power levels, all these things. They can all be characterized and monitored. If your signal-to-noise ratio for a satellite jumps from 35 up to 55, that might indicate a spoofing event, and your system should respond accordingly. Specific to autonomous vehicles, there's a number of different localization systems. There's vision-based, there's LiDAR-based, combinations thereof, and there's GNSS. These systems have got to be used together and compared to each other. We got to use those to identify divergence in the estimates, and the system needs to be able to respond when that occurs. And finally, we need to test these systems to make sure when these corner cases come up, if the GPS jumps, or if it's spoofed and somebody's, as we saw in the demo, runs the altitude through the roof for a drone. How does the system respond? In my experience, we tried to do all this. We had a simulator, tried to make sure the software would do all these things. But when we went out in the field, the system didn't always respond as we expected. And so these things need to be tested on the final systems. All right, longer term, we need to add integrity verification methods to the GNSS satellites. And this applies to all the public versions, GPS, GLONASS, Baidu, Galileo. They all need to add integrity verification mechanisms, either digital signatures, public-private keys, some other form of encryption, some way to know that the signal that your receiver receives came from the satellites in the sky, not from an SDR sitting on the side of the road. All right, so key takeaways. All right, we demonstrated, as you saw in all the videos, that you can legally spoof GNSS in a field environment. We did it using a fully enclosed Faraday cage and the ISM broadcast. One of the key things, so we were able to do a lot of cool stuff. We could move the vehicle right, move it left. We could speed it up, slow it down, delay the timing to it, cause the control system to become unstable. But that's it. There were severe limitations. When we started this, I had thought, well, hey, maybe we'll be able to have the car think it's driving down the freeway while it's parked in the parking lot. It just wasn't the case. And that's because the car uses other sensors. So GNSS is an amazing sensor, and I'm an optimist. I think it should be used for autonomous vehicles, and I'm not advocating otherwise. But we need to be careful, and we need to do it in the right way. So as I said on the last slide, specific for autonomous vehicles, we've got to combine the GNSS with other localization estimates and make sure the vehicles respond accordingly. So I had a lot of help on this project. Ben Abbott co-created the idea for this with me and helped me get the internal funding. Ben Lindau wrote most of the software and supported all the tests that you saw. Jimmy Lee did our RF design. He designed our Faraday cage and provided support when we ran into noise issues and things like that. And Matt Breeze, who didn't make my slide, but he helped with the autonomous vehicle support. And that's my presentation. Thank you guys so much for coming out. And if there are any questions, you're welcome to come up and ask. I'm going to warn people ahead of time. I do not hear very well, so please try to speak clearly. No questions? All right.
Got one.
Oh, yeah.
Curious as maybe. I'm looking ahead to.
Oh, there's one. You want to go up to the microphone? You want to go up there so that everyone can hear?
Hello?
Yeah, I was wondering if you had given any thought to what kind of the arms race would look like as red teams would inject spoofing and people would try to harden, and then what that might look like as that kind of feedback loop starts up.
Understand, I'm going to shy away from responding to nation-state style attacks. I don't. So most of my recommendations, and we're using for nation-state. There are military versions of GNSS which should be used for their systems. So all of these comments are geared towards public versions.
Can you discuss a little bit how you implemented the Faraday cage in the open field?
Sure. So the Faraday cage we bought, it's a cast aluminum box. It's very small. Inside of there, we put some RF absorbing material. Which makes it very heavy. The box has some significant weight to it. And inside there, we put the receiving antenna, and we also put our spoofing antenna. So they're the antenna. If you were doing spoofing, you take those two outside, it's going to have a similar effect. But we just put both of them inside of a box so that the signal that's being broadcast is contained.
So you put the broadcast antenna on the vehicle as well, next to the.
The broadcasting antenna is also inside the cage.
Gotcha.
Got it? Yes.
Just forgot my question. So with like the spoofing of the GNS, like, do you think that there are like, what are some other different aspects you think besides GNSS spoofing that could affect the autonomous vehicles?
That could what?
Like different attacks that could affect them besides GNSS spoofing.
Well, there's a lot of interesting work out there on sensor spoofing in general. And it's not limited to just GNSS. That's what this presentation focused on. But it's a problem for most sensors, especially those that get received data. People have demonstrated spoofing of cameras, of LiDAR, radar, ultrasonic. They've all been spoofed. Part of at least my logic and thinking is that spoofing all of these in coordination is incredibly difficult, if not impossible, with today's technology. And so I advocate for we need to have all this sensor data, and it needs to be compared with each other to do sanity checks in real time.
Do you think it would be possible if somebody put together an attack specifically on an autonomous vehicle that affected not only just the GNSS, but also like other sensors?
It's possible, but a lot of the times, and I've spent a lot of time working on this. You can characterize a lot of these attacks, and to coordinate the characterization between different sensors simultaneously, in my experience, would be just unbelievably difficult to do. Is it possible? Yes. And so, certainly if technology gets better. And if somebody has access to the data bus and you can do data bus injection and replay, maybe those things become more likely. A lot of our work has focused on the remote access to these things.
Thank you.
Hey.
We got 1 minute.
Yeah, just real quick, you mentioned at the close of your talk, you mentioned describe, if you could, other localization methods. Could you give us some examples of that, please?
Sure. So we have one that's vision-based that points down at the ground, and from the ground, it's able to estimate the position that it's at. There are other ones I'm less familiar with, but you have Waymo and you have the Chevy Cruise. Those guys have their own versions. I believe they're all camera-based, but I'm not sure. Waymo may integrate LiDAR as well.
LiDAR, thank you.
So I've got two questions. One, do you think that Amazon or any of the larger companies are looking at mitigation techniques for their drone delivery systems?
Say that again?
Have you heard of any or know of any mitigation techniques that Amazon or any of the larger commercial companies are doing for drone delivery?
I do not. I do not.
Okay. And then the second question, have you and your peers or have you talked to anybody about maybe looking at doing some similar testing against automated landing systems, takeoff systems for commercial airliners or airplanes of larger sizes?
Have not. When we were doing the research, we talked about putting it on a larger drone, which would have more, and drones have different control systems. So when we're talking about the ground vehicles, they do have to use other localization methods simply because the GNSS by itself isn't accurate enough. But drones can fly almost, you have to have an IMU with it, but a drone with an IMU can fly pretty well. So it would have different responses than the vehicles that you saw here.